Hi everyone, welcome back to another video in the Web Security Academy series. In today's video, we'll be covering a whole new topic called DOM-based vulnerabilities. This video is a technical deep dive of vulnerabilities that affect the document object model, and so it's going to be a long one. But by the end of the video, you'll have all the fundamental knowledge that is required to complete the hands-on lab exercises that we'll be covering in the upcoming videos. All right, let's get started. The agenda for today is to first provide an overview of the document object model. Then we'll go over the technical details behind DOM-based vulnerabilities. So we'll cover questions like what conditions need to be in place for an application to be vulnerable, how common are these types of vulnerabilities, and so on. Next, we'll go over how to find and exploit DOM-based vulnerabilities. So imagine you've been given an application and asked to test it. How do you go about testing the application to see if it's vulnerable? Last but not least, we'll end the presentation by discussing prevention and mitigation techniques that you can use to secure your application. All right, let's start off with the first section, which is what is the document object model? The document object model, or in short DOM, is simply a web browser's hierarchical representation of the elements on the page. Let's take an example to better understand this. We've got a minimal web page over here that displays the message Hello World. Now, this is the HTML document that makes up the web page. In the HTML document, we've got an HTML root element, a body element, and inside the body element, we've got two elements. The first one is the h1 tag, which defines the HTML heading. In our example, the text says Hello World. And the second element or tag is the p element, which defines an HTML paragraph that contains the text Welcome to my page. Now, when you open up the browser and visit the domain of this application, the browser parses and renders the HTML document. And the way it does that is by reading the HTML document and outputting its content in a tree-like structure called the DOM. Now, this structure allows programming languages such as JavaScript to access it and manipulate it. So the DOM is really just the way the web browser represents and organizes HTML information. It consists of a root node, which is the document itself, and then a series of child nodes that represent the elements, attributes, and text content of the document. In our example over here, we've got an HTML, a body, an h1, and a p element. And we've got text content in the h1 and in the p elements. Now, the nice thing about the DOM is that it can be manipulated using JavaScript, which is an integral component of how modern web applications work. So it allows you to add, change, or delete HTML elements. It also allows you to respond to user events such as clicking a button when you're submitting a form or sending a message, and so on. Now, there are many different ways of interacting with the DOM. We'll only cover a few and then we'll move on to discussing how insecure processing of DOM data can introduce vulnerabilities in the application. The first thing that you can do with the document object model is access elements. That's done using methods such as the getElementById method and the querySelector method. The getElementById method takes in an ID of an element and returns the content of the element that has that specific ID. So in our example over here, we're taking in the ID heading 1, which is the ID of the h1 element. And so the getElementById function will return the h1 element. You can also use the querySelector method, which returns the first element that matches the selector we've added as input. In our case, again, it returns the h1 element. Another way to access elements in the DOM is by directly calling the window object. That's called named access. All you have to do is call the window object and then call the ID of the element that you want to access. This specific functionality is going to come in real handy when we're talking about DOM clobbering vulnerabilities, so make sure you keep this at the back of your head. We'll talk more about it when it comes to our next section. Another thing that you could do with the DOM is modify the contents of elements. That's done through the text content and the inner HTML properties. In our example over here, we're modifying the content of our H1 element. Next, you can add or remove elements in the DOM. In this line of code over here, we're using the create element method to create a div element. And in the next line of code, we're using the remove method to remove the element that we just created. Last but not least, we have event handlers that allow the user to interact with the web page and dynamically submit or change content on the page. The example that we've got on the screen is a button that displays the text Hello World. Now, when the button is clicked, the add event listener method executes the my function, which is responsible for displaying the content of the web page. And that's pretty much it. That's a quick overview of what the document object model is and how it can be accessed and manipulated by JavaScript to introduce dynamic functionality into your application. Now that we have a good understanding of what the document object model is, let's talk about how insecure processing of DOM data could introduce vulnerabilities into your application. To do that, we need to first understand the concept of taint flow analysis. Taint flow analysis is a security technique that is used to track the flow of potentially malicious data, also known as untrusted or tainted data, as it propagates through the application. So, in simple terms, it's a technique that tracks potentially harmful data from where it enters the web application, such as user input, and it follows how it moves through the code to check if it's treated properly or sanitized to ensure that the data is not entered into a problematic function in the application that could potentially introduce a vulnerability. This is known as the taint flow problem, finding a path from the source to the sink that doesn't go through a sanitizer. The source is a JavaScript property that accepts data that is potentially attacker controlled or client side controlled. The sink is a potentially dangerous JavaScript function or DOM object that can cause undesirable effects if attacker controlled data is passed into it. And the sanitizer is a security mechanism designed to clean or sanitize input data before using it in an application to ensure that it doesn't introduce a vulnerability. So, to summarize, taint flow analysis is a technique that analyzes how data propagates from a source to a sink. Let's take a piece of code and see if we could identify the source, the sink, and the sanitizer. We've got a PHP application that has a variable called file name. The content of the variable is taken from the file name parameter in the GET request, and it's passed through a function called escape cmd shell, which is used to escape shell meta characters. The file name variable is then passed through a system function to execute the file command, which determines the type of file. So this is a program that takes an user-supplied input called file name, and it runs the file command on file name to determine what type of file it is. Our source over here is the piece of code which takes in user-supplied input, and then it passes it through the sanitizer function that escapes shell meta characters, and the sink is the system function that the source data propagates to. All right, hopefully taint flow analysis now makes sense. Now we're ready to define DOM-based vulnerabilities. DOM-based vulnerabilities are vulnerabilities that arise when a website contains JavaScript that takes an attacker-controllable value, known as a source, and passes it into a dangerous function, known as a sink. There are many different types of sources and sinks. The ones listed on the slides are the most common ones. Now, DOM-based vulnerabilities largely depend on the sink that the application is using, which is why there are so many different possible types of DOM-based vulnerabilities. We'll go over each and every type listed on the slide in the next section, but before we do that, let's talk about the impact of DOM-based vulnerabilities. The impact largely depends on the context of the vulnerability. So if the vulnerability allows you to submit arbitrary client-side code, then you could perform a cross-site scripting attack, which steals users' cookies or monitors their keystrokes or even steals their credentials by presenting them with a fake login page. However, if the vulnerability allows you to perform arbitrary cross-domain requests, then you could redirect the user to your malicious website. So the impact really depends on the context of the vulnerability. We're going to see several different types of DOM-based vulnerabilities in the next section, and with each type, we'll discuss the impact of that specific DOM-based vulnerability. Alright, in the previous section, we looked at the technical details behind DOM-based vulnerabilities. In this section, we're going to discuss how to find and exploit these types of vulnerabilities. Now, we did mention that there are many different types of DOM-based vulnerabilities, and so what we're going to do is we're going to tackle each individual vulnerability on the slide by discussing the definition of that vulnerability, the potential sinks that lead to this type of vulnerability, and the impact that this vulnerability could have on your application. And we'll start off with the first and probably most common vulnerability category called DOM-based XSS. DOM-based cross-site scripting vulnerabilities arise when JavaScript takes data from an attacker-controllable source and passes it to a sink that supports dynamic execution. Let's take an example to better understand this. This piece of code over here is from an application that has a search functionality. When you enter a term that you want to search for, it takes that as user-supplied input and sets it to the variable query. Then it calls the track search function and passes the query value as a parameter. Now in the track search function, it writes to the DOM an image element that has a source URL that contains the query string. You can see immediately over here that there's user-supplied input, so our source, that is being propagated to a sink, which is document.write. Now, there's many different ways of exploiting this vulnerability, but one of the payloads that you could use is this one over here. So we start off by closing off the source attribute and then adding our own SVG tag that when loaded presents the user with the alert box. This payload just proves that the XSS vulnerability exists and is potentially exploitable. However, if you want to show the impact of the vulnerability, you could attempt to steal the victim's session cookies or login credentials through a fake login page. You could also perform actions on behalf of the victim user and even log the victim's keystrokes. The sink that we saw in the example was document.write. However, there are so many different sinks that could potentially lead to this vulnerability if an unsanitized source makes it to one of those sinks. We'll see examples of that in the lab environment. Next, we have open redirection. DOM-based open redirection vulnerabilities arise when a script writes attacker-controllable data into a sink that can trigger cross-domain navigation. In the example that we have on the screen, the application is taking user-supplied input from the URL and setting the location object to that value. This can be exploited by an attacker to send the victim user to a malicious site that the attacker controls. Now again, there are many different sinks that could lead to this vulnerability. The location object is just one of them. Let's move on to cookie manipulation. DOM-based cookie manipulation vulnerabilities arise when a script writes attacker-controllable data into the value of the cookie. In the example that we have on the screen, we can see that JavaScript writes data from the source window.location to the sink document.cookie without sanitizing it first, and so an attacker can exploit this vulnerability to manipulate the value of the cookie and inject arbitrary values. The sink that could lead to this type of vulnerability is document.cookie, and the impact of this vulnerability largely depends on the role that the cookie plays in the website. So depending on the role, it could lead to things like cross-site scripting attacks, session fixation attacks, performing unintended actions on behalf of the user, and so on. Next, we have JavaScript injection. DOM-based JavaScript injection vulnerabilities arise when a script executes attacker-controllable data as JavaScript. In the example over here, the application is taking client-supplied input and passing it unsanitized into a dangerous function called eval, which evaluates JavaScript. Now, in the example, the eval function is the sink, but again, there are many different sinks that could lead to this type of vulnerability. The impact of this vulnerability is that the attacker can execute arbitrary JavaScript input in the context of the user's browser session. So this can be used to perform an endless list of actions, starting from stealing the victim's session tokens to logging the victim's keystrokes. Next, we have document domain manipulation. Document domain manipulation vulnerabilities arise when a script uses attacker-controllable data to set the document domain property. So our sink over here is the domain property. Now, this vulnerability may be exploited by an attacker to fully compromise the victim website. However, it is important to note that browsers usually enforce some form of restriction on what the document.domain value could be set to. So it's not as easy as just setting it. There are certain things that you could do to allow it to change the domain property to a completely unrelated domain. However, the technical details behind this specific vulnerability are beyond the scope of this course. All right, let's move on to WebSocket URL poisoning. DOM-based WebSocket URL poisoning occurs when a script uses attacker-controllable data as the target URL of a WebSocket connection. This type of vulnerability could allow an attacker to construct a URL that, if visited by another user, will cause the user's browser to open a WebSocket connection to a URL that is under the attacker's control. Now, this could lead to many things, and it really depends on how the website uses WebSockets. If the website transmits sensitive data from the user's browser to the WebSocket server, then the attacker may be able to capture that data. However, if the application renders the data in the browser, then the attacker may be able to use this vulnerability to perform client-side attacks such as cross-site scripting. We have an entire module just dedicated to WebSocket attacks. All right, let's move on to link manipulation. DOM-based link manipulation vulnerabilities arise when a script writes attacker-controllable data to a navigation target within the current page. So for example, using the href attribute, or the src attribute, or the action attribute. Now, the attacker could use this vulnerability to perform a variety of attacks. The most obvious one is redirecting the user to an external domain, which can be leveraged to submit sensitive form data to that domain. You could also use it to change the file or query string associated with the link, causing the user to perform an unintended action that could potentially cause harm to that user. Moving on to AJAX request header manipulation. DOM-based AJAX request header manipulation vulnerabilities arise when a script writes attacker-controllable data into the request header of an AJAX request that is issued using an XML HTTP request object. So the sinks for this specific vulnerability are the set request header, the open, and the send methods for the XML HTTP request object. Another potential sink is the jQuery.global eval function. Now, an attacker could use this vulnerability to manipulate the headers that are processed in the AJAX request, so the impact largely depends on the role of those headers in the application. Next, we have local file path manipulation. DOM-based local file path manipulation vulnerabilities arise when a script passes attacker-controllable data to a file handling API as the file name parameter. The following are the potential sinks for this specific vulnerability, and the impact depends on how the website uses the file that is being opened. If the website reads data from the file, then the attacker may be able to read that specific data. If the website writes specific data to a sensitive file, so think of it as maybe a configuration file, then the attacker may be able to write to that file. So the impact really depends on how that file is being used in the application. Next, we have client-side SQL injection. DOM-based client-side SQL injection vulnerabilities arise when a script incorporates attacker-controllable data into a client-side SQL query in an unsafe way. A potential sink is the JavaScript database function execute SQL. Now, the impact of this vulnerability depends on the website's usage of the SQL database. If the database stores sensitive data, then the attacker may be able to retrieve that data. If the database is used to store pending user actions, then the attacker may be able to modify these actions. Moving on to HTML5 storage manipulation. HTML5 storage manipulation vulnerabilities arise when a script stores attacker controllable data in the HTML5 storage of the web browser. So that would be either in local storage or session storage. The sinks for this vulnerability type is the setItem function for the session storage and the local storage objects. Now, the impact largely depends on how the website uses session and local storage. If it reads back from it and renders its content in the browser, then it could potentially lead to cross-site scripting vulnerabilities. If it's used in a different way, then the impact will also be different. Moving on to client-side XPath injection. DOM-based XPath injection vulnerabilities arise when a script incorporates attacker-controllable data into an XPath query. The potential sink for this vulnerability is the evaluate function in the document and element objects. The impact, again, depends on how the query results are being used. Depending on how it's used, the attacker may be able to subvert the website's logic or cause an unintended action on behalf of the user. Moving on to client-side JSON injection. This is really similar to XPath injection with the exception that our attacker controllable data is getting inputted and parsed as a JSON data structure and then processed by the application. Alright, next we have DOM data manipulation. DOM data manipulation vulnerabilities arise when a script writes attacker controllable data to a field within the DOM that is used within the visible UI or client-side logic. The impact of this vulnerability could be minimal to severe depending on the sinks that we're dealing with. At a lesser end, the impact could be just the defacement of the vulnerable application, but on a more severe case, if the sink is the source attribute, then you could potentially perform actions on behalf of the user. Let's move on to denial of service vulnerabilities. DOM-based denial of service vulnerabilities arise when a script passes attacker-controllable data in an unsafe way to an API whose usage could cause the user's computer to consume excessive amounts of CPU or disk space. This obviously causes denial of service attacks in the user's browser, and the potential sinks for this vulnerability are the request file system and the regexp or regular expression function. Now, this attack vector for this specific vulnerability is very interesting. It involves giving the application a regular expression that exhausts the computing power or memory of the device. Again, it's beyond the scope of this course, but there are a ton of resources online that you could read up on if you're interested in how this vulnerability works. All right, let's move on to web message vulnerabilities. DOM-based web message vulnerabilities arise when a script sends attacker-controllable data as a web message to another document within the browser. The sink over here could be any functionality in the DOM that is used by the incoming message event listener if the application accepts web messages from an untrusted source. Now, the impact depends on how the document accepts messages. If it accepts arbitrary messages, then it could potentially lead to client-side attacks, such as cross-site scripting. Last but not least, we have DOM clobbering. We're going to spend quite a bit of time on this specific vulnerability type because 1, it is usually overlooked in pen tests, and 2, statistics from the studies that have been done show that many of the applications in the wild are vulnerable to DOM clobbering. So it's really important to understand how this vulnerability works and how to find it in an application and exploit it. But before we define it, let's revisit how elements are accessed in the DOM tree. There are two ways to access elements. The first one is referred to as the clean way, and the second one is referred to as the dirty way. The clean way involves using the getElementById or the query selector methods. The dirty way involves using property access on the window or the document objects to directly access an element. Let's take an example to better understand this. In this example over here, we have an HTML document that has a form element that has a name attribute that is equal to X. In the form element, there are two child input elements. One of them has ID Y and the other has ID Z. Now, our goal over here is to access the input element that has ID Y. This can be done in two ways. The first one, or what we refer to as the clean way, is that you could use the getElementById method or the query selector method in JavaScript and pass the ID of the element as input. The dirty way is to directly access the element using either the window or the document object. So you could say document.x, which references the form element that has name x. And then if you say document.x.y, then it references the child input element that has ID y. Another way of doing this is by just saying window.the ID of the element that you want to locate, which again in this case is y. This way of doing things is known as named access on the window or the document objects in the HTML specification, and DOM clobbering exploits this specific rule. Let's take a code example to see how this works. In our application, we have a script that runs this code over here when the page is loaded. It starts off by creating a variable called SumObject, and it uses the logical OR operation to set the value of the variable. So if the value is already set, then it'll just take that value. Otherwise, it'll set the variable to nothing. And then it goes on to create the script tag and then sets the source attribute for the script tag to the URL attribute of the SumObject object. And then it appends the script tag to the DOM. Now, if we're allowed to enter HTML into an application, let's say through a comment feature, then we can control what this value is set to and eventually control what gets added to the document object model. The way we're going to do that is by clobbering a global variable or property of an object and overriding it with a DOM node or an HTML collection. For this specific example, the way we're going to exploit this is by adding two anchor elements that contain the same ID as the object that we want to clobber. Now, when you have two anchor elements with the same ID, the DOM is going to group them into something called an HTML collection. This is just an array of values. And so when the page is loaded and it runs this piece of code over here, it will attempt to retrieve the object SumObject. However, that was overwritten by our exploit code, and so it'll retrieve it from the HTML collection, which contains the object SumObject with the URL attribute set to the malicious site that contains a malicious JavaScript that will end up running in the application in the user's browser. And that's how DOM clobbering works. So essentially, it's a namespace confusion vulnerability where attackers inject codeless HTML markup and transform it into executable code by exploiting the interaction of the code with the runtime environment. There are a ton of real-world examples where DOM clobbering vulnerabilities were either identified or exploited. A really famous example is Gmail in 2019. Gmail has a dynamic mail feature that allows you to include dynamic content such as HTML into your email. Now, the way it worked is Gmail dynamically created the script that is responsible for this functionality, and the SRC attribute value came from window.test location, which can be clobbered with codeless markup by an attacker, just like we saw in the previous example. Now, they did have a sanitizer. However, the sanitizer did not block this markup because it didn't contain any JavaScript. It was simply HTML, and so the sanitizer failed. But the one thing that did stop this vulnerability from being exploitable is that they had set content security policy rules to disallow the execution of scripts. And so, if we were to exploit this, like we did in the previous example, we would clobber the SRC attribute and add a link to a malicious script that, when run, would execute in the application in the user's browser. However, because of the CSP rules, the script was not allowed to execute, and so this vulnerability was not exploitable. Now, there are multiple HTML and DOM specification rules that you can abuse to perform DOM clobbering attacks. In the previous example, we made use of the first rule named access on Windows and the fifth rule, HTML collection, to clobber the SomeObject SRC attribute in the example. However, there are other combinations that you could use. So, for example, you could use the first one, named access on Windows, in combination with the third one, which makes use of the parent-child relationship inform elements. You'll get hands-on experience in both cases in the lab environment. Now, DOM clobbering is a whole topic on its own that could take hours to explain, and we really just scratched the surface in this presentation. So I would absolutely recommend that you check out this presentation if you're interested in learning more about this topic, and I've got the link to the presentation on the slides and in the description of the video. All right, we went over many different types of DOM-based vulnerabilities. In the next couple of videos, you'll gain hands-on experience exploiting several of those vulnerabilities in applications that model the real world. Of course, we can't end this section without mentioning web application vulnerability scanners, which are automated tools that crawl your web application and look for vulnerabilities. I personally use Burp Suite Pro. However, there are many free and open source options that you could start out with. I do find scanners to be really useful when it comes to identifying DOM-based vulnerabilities, and so you should definitely be running an automated scan on your application and also complement it with manual testing. All right, let's move on to the last section, which is how to prevent DOM-based vulnerabilities. The most effective way to avoid DOM-based vulnerabilities is to avoid allowing data from any untrusted source to dynamically alter the value that is transmitted to any sink. Of course, this is not always possible, and so you can use a combination of defenses to minimize the likelihood of an attack from succeeding. The first defense is to validate data on a whitelist or an allow list basis, so only allowing content that is known to be safe. The second defense is to sanitize or encode data. Now, depending on the output context, this might require applying combinations of encoding schemes. So there's HTML encoding, URL encoding, JavaScript encoding, and CSS encoding. You absolutely should not implement your own encoding library. Instead, you should use an existing well-known secure library. Now, those are the general defenses. There are specific prevention mechanisms that you could use to prevent specific DOM-based vulnerabilities. And we learned about many different types of DOM-based vulnerabilities. And so this prevention column over here is unique to the specific attack vector that is written. So for open redirection, you want to avoid dynamically setting redirection targets using data that originated from any untrusted source, so that the attacker could not exploit this vulnerability to send the user to a malicious website that the attacker controls. For cookie manipulation, you want to avoid dynamically writing to cookies using data that originated from an untrusted source. For JavaScript injection, you want to avoid allowing data from any untrusted source to be executed as JavaScript. For document domain manipulation, you want to avoid allowing data from any untrusted source to dynamically set the document.domain property. For WebSocket URL poisoning, you want to avoid allowing data from any untrusted source to dynamically set the target URL of a WebSocket connection. For link manipulation, you want to avoid allowing data from an untrusted source to dynamically set the target URL for links or forms. So make sure that untrusted data cannot change the source attribute or the href attribute. For web message manipulation, you want to avoid sending web messages that can contain data that originated from any untrusted source. And then when you're sending cross-origin messages, explicitly specify the target window and verify the origin of any incoming messages. For AJAX request header manipulation, avoid allowing data from any untrusted source to dynamically set AJAX request headers. For local file path manipulation, you want to avoid allowing data from any untrusted source to dynamically pass a file name to a file handling API. Next, we have client-side SQL injection. To prevent this attack vector, you want to make sure that you use parameterized queries for all database access. And it's strongly recommended that you parameterize every variable data item that is incorporated into the database, not just the ones that come from untrusted sources. For HTML5 storage manipulation, you want to avoid allowing data from any untrusted source to be placed in HTML5 storage, such as session storage and local storage. For client-side XPath injection, you want to avoid allowing data from any untrusted source to be incorporated into XPath queries. And for client-side JSON injection, you want to avoid allowing strings containing data from any untrusted source to be parsed as JSON. For DOM data manipulation, you want to avoid allowing data from any untrusted source to be dynamically written to DOM data fields. And for denial of service, you want to avoid allowing data from any untrusted source to dynamically pass data into problematic platform APIs that could potentially exhaust the CPU and disk space of the user. For DOM clobbering, there's a few things that you could apply. So check the objects and functions that are in use, make sure that they're legitimate, and avoid bad code patterns. So using global variables in conjunction with the logical OR operator should be avoided. We saw an example of that led to a DOM clobbering vulnerability. And make sure that you use a well-tested library, such as the DOM Purify library, that mitigates several different types of DOM clobbering vulnerabilities. And that's pretty much it. So make sure that you use the general prevention mechanisms first, and then depending on the technologies that your application is using, make sure that you use the specific prevention mechanisms as well. All right, we've reached the end of the presentation. I have a few resources that were used to build this presentation and a few others that could be really useful if you're interested in learning more about this topic. The first two are the Web Security Academy, so Portswigger resources, and this is essentially the two resources that majority of this presentation is based on. So I absolutely recommend that you look into at least the first resource. The second resource over here is the list of labs that we'll be covering in the next upcoming videos. The third resource is a PowerPoint presentation on tainted flow analysis. So it goes over what taint flow analysis is. It also goes over several code examples and identifies the sanitizer, the source, and the sink for each code example. So it's definitely an interesting resource if you would like to learn more about taint flow analysis. The remaining resources are about DOM clobbering. This is not an easy topic. It's also quite overlooked in pen tests, which is why I included several resources on this topic. I've already mentioned this in the presentation, but the first resource you should look at when it comes to DOM clobbering is this presentation over here, which talks about the technical details behind DOM clobbering vulnerabilities, talks about how rampant it is in modern web applications, and then talks about the tool that they developed and a resource that they developed that identifies DOM clobbering vulnerabilities. So make sure you check it out. And that is it when it comes to resources for DOM-based vulnerabilities.